In today's lesson, I'm going to discuss several examples of derivative, and these examples will center on the derivative as a rate of change. One common application of derivative as a rate of change is that of distance. Normally, we label distance as letter S, although we can think of it as D, but since we are using derivative and common to the expression, or the common expression that we use for derivative is D, we will assign S for distance. So what is it all about, distance? These are the things that I want you to keep in mind. The relationship of velocity and the distance, so let this V and this is S, is that the velocity is the derivative of distance with respect to time. In the same way that acceleration to velocity, the acceleration is the derivative of the velocity with respect to time. So that means if given the situation that the distance function is given by, say, any function of time, say t cubed plus, or say minus 60 squared plus 90, if I want to find the velocity of a certain object given this distance equation of an object at a particular time, has to be a particular time, then all I have to do is to find the derivative of the distance with respect to time. Let's say, for example, if I want to find the velocity of this object at t equals 2 seconds, meaning after 2 seconds of traveling, then to find the velocity, we simply get the derivative of S with respect to time. And using the basic rules on differentiation, this will become, or the function f of t, which is the distance function, will become 3t squared minus 12t plus 9. And that every time a question is being asked what is the velocity at a particular time, all we have to do is to find ds over dt at a given t. As with our example, we want to find the velocity at t equals 2. So that means at t equals 2, then ds over dt is equal to 3 times 2 square minus 12 times 2 plus 9, which is equal to, so this is equal to 3 times 2 squared, so that's 4 times 3, 12, minus 2 times 12 is 24, plus 9. And then 12 minus 24 is negative 12, plus 9 is negative 3. That means the velocity of an object is 3, say if the unit is meters for the distance, and say the time is in seconds, then the velocity is negative 3 meters per second. Now, take note that when we are talking about velocity, the negative sign of the velocity is giving us the direction of the object. So if the initial direction of the object is going to the right, at t equals 2, after 2 seconds, the object is moving in the opposite direction and its speed is 3 meters per second, meaning it will change by 3 meters per second at that moment. Okay, so it's like when so expect that after another second the distance will be changing by 3 meters. That's the meaning of negative 3 meters per second. So again, what you need to keep in mind is the relationship of velocity and the distance, and acceleration and velocity. The velocity is the derivative of distance with respect to time, and acceleration is the derivative of velocity with respect to time. Okay. Now let's take a follow-up question using the same function. Suppose we want to find when is that object be at rest. Okay, so at rest in a distance velocity acceleration question, at rest means the object is not moving. So when the object is not moving, that means the velocity is equal to 0. So given that the distance is equal to t cubed minus 60 squared plus 90, and we found the velocity, which is the ds over dt, to be 3t squared minus 12t plus 9, then we can see that the object will be at rest when the velocity is equal to 0. In other words, when 3t squared minus 12t plus 9 is equal to 0. So to find the time when the object is at rest, all we have to do is to solve this equation. So solving this equation, this is a quadratic equation. First, we could see that we have a 3, a 12, and a 9. These numbers are divisible by 3. So if we divide both sides by 3, then the equation will become t squared minus 4t plus 3 equal to 0. And factoring this will give us t and t, 3 and 1. I need a negative and a negative. So t minus 3 is 0, or t minus 1 is equal to 0. And that means t is equal to 3 or t is equal to 1. In other words, the object is not moving or at rest after the first second, after 1 second, and after 3 seconds. Okay, so that's another possible scenario in which a velocity distance problem can be given. Now let's take some examples on acceleration. So suppose I ask you, I want you to find the acceleration A after 4 seconds, so meaning that t is equal to 4 seconds. So if we know the relationship of acceleration and v when it comes to derivative, and that acceleration is dv over dt, then all we have to do is to find the dv over dt. We already have v, which is equal to 3t squared minus 12t plus 9. So dv over dt is simply 6t minus 12. And this is the acceleration. So at t equals 4, then dv over dt is simply 6 times 4 minus 12, or 24 minus 12 equals 12. So the velocity, the acceleration is 12. If we use the units that we assign, this is meters per second squared. So the acceleration, so the velocity is changing at the rate of 12 meters per second squared. Okay? So in this example, you already have like the idea of the relationship of velocity and distance and acceleration and velocity. If we talk about acceleration and distance, one should see that if v is ds over dt and a is equal to dv over dt, what is a with respect to s? Okay, if we will look at the relationship, it should be clear that acceleration is the second derivative of distance with respect to time. Because when we get the velocity, we get the derivative of distance, and to get acceleration, we differentiate v, so it's like we're taking the second derivative of the distance. Hence, acceleration is the second derivative of distance. Okay? So I hope you understand our first example on derivative as a rate of change. In another video, I'll be explaining more examples of rate of change wherein the problem is no longer about velocity, distance, and acceleration. Okay, but for now, keep in mind that the idea will revolve on the relationship of velocity and distance and acceleration velocity under derivatives. Okay, that's it.